Hi, welcome to another video. So first of all, I'm in the car, haven't got a separate microphone, so hopefully this Sony camera will record the audio correctly. Today is the 14th of May 2017. I've been promising a couple of you guys to do a second video on CAN communication. So today I'm going to concentrate specifically on CAN communication on a car and just give you the basics. So what I've got here is a cheap old maxi-scan OBDII, so onboard diagnostics is sort of second edition, and EOBD is European onboard diagnostics. I think this was like, I don't know, 15 quid or something from years from eBay years ago. Didn't work on my 2001 Peugeot because the diesel European onboard diagnostics didn't really become established until 2003. Petrol was a year earlier or before that. So this is a Peugeot 309. In case you're wondering where the diagnostics is, pull out a little rubber mat down here and stick the data link connector in there. This has actually got a fault that comes up on this display. I might show you later if I have time. So I've connected the OBD, onboard diagnostic connector, data link cable, that forward column. Got my scope, my trusty Keysight oscilloscope running there. I'll just lock this tripod off. So this Keysight oscilloscope, it's serial decode enabled, and no, I wasn't given the software by Agilent or Hewlett Packard or Keysight. I had to buy it a few £100 a number of years ago. So I've been doing some research on this car. There seems to be something like 16 odd computers or 16 separate identifications. For example, here we've got the engine 208. There's another one there, 228, not sure what that is. I'd need to speak to a decent service technician. He'd be a Peugeot service technician. He might be able to tell me what 228. I've got a list here. So this is a regular 308 2009, and hopefully you can see there, hopefully the camera will focus. There's roughly 16 identifications coming up. So if you haven't seen the other video and you want to know how the CAN communication works, go and have a look at the other video. This is obviously going to be a new one. These are 16, roughly 16 identifications. Now they don't use the 28-bit extended identifier. They just use the 11-bit, so that's easy. 11-bit probably because they're all 3-digit numbers. So going from the other video, because the engine has the lowest number in the arbitration field, it's if more than one control unit is going to try and communicate, the engine is going to win, and I explained that in the other video. So there's 208, we've got a second ECU here on the scope, 228, no idea what that is, but I started running through, there was data coming from everywhere, and I narrowed it down to that the engine was 208. So if you've got a PIC microcontroller or an Arduino, something like that, you could program it to ask 208 for the current data or stored data, that sort of stuff. That's where that's where you'd start. You need to know the ID of that engine control. So 11-bit ID, not the extended frame. Let me show you the scope, give you a couple of examples. Right, I apologise for any glare coming off this camera, but I'm outside and it's quite a bright day today, so I can't odds that. You can see if I turn the scope up a bit, just that white out, so apologies for any glare. So if I bring this time base out a bit, so I'll get rid of this other ECU here. We're concentrating on just the engine. Now what I said to some of you guys in the previous CAN tutorial, I said I didn't have time to explain all these, this is the CAN high, this is the CAN low, but I didn't have time, or I forgot why I drew them slightly slanted curves, or why I drew them with slanted lines. So if I freeze this and expand this out, so once you zoom into these bits, you can see they're slanted, so they actually take time to turn on and off. So it's generally accepted when you draw something, draw a signal, it can't switch on instantaneously. There's a delay, So I've figured out this CAN system on this Peugeot 308 runs about 500 kilobits a second, and if you look at the time base here, we are on 250 nanoseconds a division, so it's 250 nanoseconds from there to there. So it is switching on fast. Bring it back into the middle. Right, so we're on 100 nanoseconds a division. So you can see, I don't know what these glitches are. Probably just the load on the CAN line with all the different ECUs. But those the termination resistors, as I said before, affect these times and how square the on time and off time is. But so that's why I drew the signals in the shape I did and not square, because in reality they're not square. So I can't believe the sun has come out, making this glare even worse than it was before. Right, so we are looking at one complete frame. So 11-bit ID, that's the ID for the engine on this Peugeot 308. We've got a data length code of 8, so we're sending, well, the engine is sending 8 bytes of data. But if we look into this data and play about with the car, it will start to mean something. This figure at the end, as I said before, that's the cyclic redundancy check. So the transmitter sends that cyclic redundancy check. It's a pair of two bytes. So 16 bits of data to signify the value of all these bits. And the receiving node will also calculate the cyclic redundancy check data. And if the two tally up, all well and good. If the receiver says it should be a different value, it will throw up a CRC check error. Right, so the ignition is turned on, but the engine is off. So these 2 bits are the engine RPM. This 6A, if I refer to my notes, and I've lost it. Well, the third hex seems to look at the fuel status, which have a look on Wikipedia as well, and Google. That third byte seems to be the fuel status. So at the moment it's 6A with the engine off. With the ignition off, it changes to 25. Hopefully this camera is going to pick it up with this sunshine on the screen. Turn the ignition back on, and if I start the engine, you'll see this number change. This bit here is 0C, so the engine's not running. If I press the brake, you see it goes to 0E. Not sure about these 2 bits at the moment. This 25 at the end, the last byte, that seems to change to 26 when the engine's running. But it's these first 2 bytes. So because obviously hex, so numbers from 0 to 255, not going to give you enough numbers to work out your revs if it goes up to, you know, 7,000 to 8,000 revs. So the revs are split into 2 bytes, and you just simply add that one and add that one, and possibly divide it by 4, but we'll have a look later. But so if I start the engine, so the ID doesn't change, so all those first 11 bits are staying the same, and you can see these other bits up here for the engine revs. They're creeping up and down as the idle settles. If you don't know how this is counting, have a look at one of the links I put in the previous video. Have a look at the SPI, and I show how an 8-bit SPI counts. So this CAN isn't transmitting the clock. The receiving nodes look at the signals coming in and synchronize with it. And so with its own internal clock, it can work out the data here, and what's a 1 and what's a 0, that sort of stuff. Have a look at SPI, my SPI counting video, if you're not sure. That's constantly changing with the revs. If I rev it up to 2,000 revs, so that's roughly 2,000 there. We've got 3E, well that's roughly 2,000, so what have we got? 3F, no, it's creeping up. trying to look at the scope and the rev counter. We're on 1900 there, just over 2000, roughly there, 2000. So 3D, call it C0. We'll have a look at that. 3D C0. That's the revs. I think I worked out one of these. If I turn the ignition off again, just to steady that can, turn the ignition back on before it stops communicating. Right, so this one here, 1, 2, so that revs, not sure, oh, fuel status. This one here, if I touch the throttle, C8 down to 00, so I'm not touching the throttle, and that's full throttle. So 0C, if I press the brake, goes to 0E. Haven't figured out the FF. Let me start the engine. It could be the vehicle speed. And I can't move because I've got a mains cable running to this car, running this scope. So it's staying at nothing, so that could be the vehicle speed. And obviously the cyclic redundancy check. So I've synchronized this scope. Seeing, yeah, I found the ID of the engine, I think that's 208. I've got this scope to trigger on anything beginning with 2. So if I bring in this other field, actually that 26 as I rev it up. So that could be throttle engine load. Yeah, that could be engine load. That's still not moved, so maybe vehicle speed. And then bring in this other one. So this other one, 228, don't know what it is. It's another module on the car, but that's only sending data length code of 4, so that's sending 4 lots of data. Yeah, that's the onboard diagnostics. I took it apart earlier. That's the power and ground, or that's power, that's ground. So I've grounded, this car is actually grounded through the scope and through the 20 metre extension lead running into the house. And I'm just picking up the can high and can low down there. Right, now I've taken that synchronization to that 208, taken it off so that we can look at all the ECUs communicating. And so obviously the engine has priority, but all these other ECUs, I've no idea why there's so many. As I say, there's 2009 car, maybe one for the radio, one for the steering column switches, maybe one for the clock. It's sort of entertainment, climate control, doors, ABS, everything. So if I just freeze that, there's 3 ECUs caught, and none of them are the engine. And you can see that that one's sending 3 bits of data, 6 bits of data. So I'm just triggering the scope, so it just, stops at random parts. Right, so look, we've got 1, 2, 3, 4, 5, 6, 7 ECUs talking there. And you can see the data field, 8 bits, 8 bits, 8 bits, 7, 8, 4, 8. Maybe that one's a radio. Radio wouldn't need to transmit much data. Right, I'm inside. While I convert those videos I've just done, I didn't have time looking at the car and the scope, looking at the fault codes. Now there's various standards on when you connect an onboard diagnostic like scanner. There are standards on what you should be receiving, and 2 of them are ISO 15765-4 or -4 and SAE J2284. So they say if you've got various faults, like specifically like this engine, so P is for powertrain. I think that's probably an American term, but anyway, powertrain for engine. The generic fault codes are down here. So, for example, P01XX, that's fuel and air metering. P00XX, fuel and air metering plus auxiliary emission controls. Then further down, fuel and air metering injector circuit if it's a 2. Hopefully it's still on the camera. P03 XX ignition system misfire. And then auxiliary emission control. And if I haven't got this camera on a tripod. You've got the 5 for vehicle speed and idle controls, computer output is number 6, and P07 and 8 are for transmission faults. So the XX, that's obviously going to give you 99 combinations. So presumably, when you've got specific diagnostic software, whether it's Ford, Peugeot, any manufacturer, they'll go into specific faults. These are generic, and then you'll get a specific fault identifying, a specific fault on the vehicle. So, if you've got a Ford, the wire behind the Ford badge is broken. Something silly like that. But you'll have specific faults with specific manufacturers' software to read the faults. These are just generic. That these standards people, fortunately, the manufacturers have to comply with these standards. Otherwise you'd be screwed. You'd have to pay dealers exorbitant prices to go and get a simple fault checked. So if you have got a late vehicle and you fancy having a look yourself, pick yourself up a scanner from as little as £15 and you can put it on and it will put you in the right ballpark. So my specific Peugeot has got P0490 auxiliary emission control, and the 90 refers to this emission control, but then more specifically it's referring to the exhaust gas recirculation valve. It's saying it's possibly clogged or not opening, which could be a vacuum line. Unfortunately, the EGR valve is buried down the back of the engine. Turbo's nice and easy to get to on these 1600 turbos, but the auxiliary emission control, buried. So I don't know if I'll have time to have a look or just give it to a friendly garage I know with reasonable labour rates. So P0490 is something to do with the EGR. It gives you a rough idea. Right, hi. For those of you who haven't seen my programming videos and you're new to this can, maybe you're not familiar with hexadecimal counting. So why do we use hexadecimal and not decimal? Normal 1, 2, 3, that sort of stuff. Well, basically, because hexadecimal, in 2 digits, 2 characters, you can get a value of 255 or 256 in human English, 255 in 2 spaces instead of 255 in decimal is obviously 3 spaces. If you want to work it out, pull up Windows Calculator, go standard, change it from the standard view down to programmer, and put in your hexadecimal there. Hopefully you can see it with this camera. I'm not zoomed in very far. Hexadecimal, decimal, octal and binary. So it's a little confusing because 1 to 9, whether it's English or computer code, is 1 to 9, but hexadecimal, if I start at 9, if you're not familiar at all, so we get 9 in decimal, which is 9 in hex, then plus 1 equals, so it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So that gives us 16 just using 1 character. So plus 1, C, plus 1, and then finally plus 1 equals F. So if you look at this, so that's the highest 1 digit in hexadecimal, F. But you see there, what's confusing, it's actually 16 in like human language, but we've got decimal 15, and that's because in computer language we don't, if we're counting with a finger, we go 1, 2, 3, 4, 5. In computer code, we've just missed out the 0. So 0 is a useful number. So we go 0, 1, 2, 3, 4. So all of a sudden, yeah, we've only counted up to 4 using 5 spaces. Yeah, 0 is a number. So 255 in hexadecimal, I'll show you it's FF. So cancel, click on hexadecimal, go FF, and you'll see there 255. So 255 is a full 8-bit register, an 8-bit FF, 255, and then binary 11111111. So another quickie, so throttle position sensor, you'll notice we measured from 00 to C8 was maximum throttle. So bring up the calculator again, switch to programmer view. So we had 00, change to hex up here, we had C8, and look, in decimal we've got 200. So the computer and the microcontrollers inside are splitting that full throttle movement into 200 pieces. So it can increment the throttle, you know, anywhere between 0 and 200. That's the digital value. In hex is C8. But so, you know, C8, that's 2 characters, whereas normal decimal, that's 3 characters. So, you know, that's why we use hexadecimal. It's short, yeah, smaller, takes up less room, and that's easy for the memory. That would just take up 1 byte in the memory. So that's obviously all the ECUs talking independently of one another. Each relevant ECU is listening to what particular ECU you should listen to. Obviously the engine, I don't think it's going to listen to the radio if the radio has a message, that sort of stuff. So that's they're all talking at once, and it's difficult to see. So, you know, synchronize into one ECU and look at what it's saying. That's obviously the Peugeot, the manufacturer's computers. That's what they do. They would know the identification of each particular ECU. Go in, look at the codes, look at the stored data, program it if necessary, that sort of stuff. So that's a sort of basic rundown and a live look at the CAN on a Peugeot 308 from 2009. Hopefully that makes a bit more sense. So, you know, this makes no sense to anyone. Lock it to the engine, look at the data, throttle, RPM, that sort of stuff, and it starts to make more sense. Hopefully this has helped. Thank you very much.